yesterday we started talking about how to find the force between two charges, and we said it's very similar to what we do for gravity. For gravity, the force depends upon the product of the masses and the distance between the two masses. And for charges, it depends upon the product of the charges. We use Q's to represent the charges and the distance between the charges. And is that about the last thing you guys have in your notes? And I think we talked maybe about the fact that K would be a lot bigger, that this constant for electricity would be a lot bigger than G was for gravity. A couple other things that are important here. This equation assumes that the two charges are very, very tiny. It assumes that they're point charges. It assumes that they're point charges. Now, in reality, nothing is the size of a point. You understand that? But if the size of the charges themselves is small compared to the distance between them, we can get away with saying they're point charges. And as an example of that, I want you to consider, let's say we take Alex and Grant, and we give them both a charge. And let me draw a picture of this. Right, here's Alex, and here's Grant. And let's say they're maybe 2 meters apart. If we charge them up, they are not point charges, right? They're fairly large compared to the distance between them. On the other hand, if we make them like 1,000,000 miles apart, take them out in space, one's here and one's way over there, 1,000,000 miles between the two, then is their physical geometry going to matter much compared to that distance? If I try to draw it on that scale, the size of each one of them would be pretty much a point. And that's what we're talking about. Point charges are things that are really, really tiny compared to the distance between them. The other thing that Coulomb's law works for besides point charges are spherical objects. As long as the charge is evenly distributed along the sphere, we can get away with using Coulomb's law for spheres. If we measure the distance between them from where to where? Mm-hmm. Yeah, if we go from the center of the one charge to the center of the other charge, we call that distance r. Again, it works. So they've either got to be very tiny or they've got to have spherical charge symmetry to be able to use Coulomb's law. Here's a case where it doesn't work. It's fairly common to have two metal plates, one of which is positively charged, one of which is negatively charged. Call that arrangement a capacitor. But if you wanted to find the force that the one plate exerts on the other plate, you could not use Coulomb's law to do that, because these two flat plates are not point charges. And if you think about that, what would you use for R if you were going to do that? I mean, if you look at how far this charge is away from that charge, that's completely different than how far it is away from that charge, isn't it? And that maybe will help you to see why Coulomb's law doesn't work for those types of situations. Whereas for a point charge, all of the charge is the same distance away from the other charge. Or for spherical charge symmetry, as long as we go to the very middle of it, for every charge that's closer, there's charge that's further away. It averages out to be right to the center. All the calculations we're going to do are going to be for point charges, but I want you to be aware of the fact that they've got to be point charges or spherical symmetry. And R we already talked about. K, the constant, I don't think I gave you that yesterday. Value for it is 9 times 10 to the positive 9th Newton meters squared per Coulomb squared. Remember what G was? G was 6.67 times 10 to the, remember? Yeah, negative 11th. And this is positive 9th. Right, so that tells you how much bigger electrical forces are than gravitational. So let's take some examples of calculating some electrical forces and understand that the Coulomb is a very large unit of charge. So because of that, oftentimes we talk about microcoulombs or nanocoulombs or picocoulombs. Right. Yeah, question?
Just what's the units for the 9 kilotons?
Oh, Newton meters squared per Coulomb squared. Yeah. Now, if you remember back to the units for capital G, they were Newton meters squared per kilogram squared. So the Coulomb just takes place of the kilogram. Other than that, it's the same. But since the Coulomb is a very large unit, usually we're going to be working with charges that are smaller than that. So it's typical to see microcoulombs, and micro is 10 to the negative 6. Nanocoulombs, remember these prefixes from way back at the beginning of the year? No. Nano is 10 to the negative 9th. And you'll even see picocoulombs. Pico is 10 to the negative 12th. Right, so as you start working through the WebAssign problems, those conversions will be useful to you. Even that Van de Graaff generator, when I had that thing charged up, we're only talking about, I think, microcoulombs of charge. Right? It's not a lot, which is a good thing. If it were a lot and you touch it, you could get killed. Seriously, I mean, a coulomb of charge passing through your body would be enough to do you in. But the charge in that's way, way low. So it kind of scares you when you touch it, but it doesn't cause any bodily harm. So here's the problem we want to work. We have 3 charges, Q1, Q2, and Q3. Q1 and Q2 are both positive. Q3 is negative. All right, so take a minute to jot down the configuration here. Notice it gives you the distance between the charges. All right, so Q1 is positive 1 microcoulomb. Q2 is positive 2 microcoulombs. And Q3 is negative 3 microcoulombs. And everything's a meter apart. And the problem is find the force on Q1 due to the other 2 charges. And we're assuming that all these are point charges. Right? They're tiny, and they're also spherical. And the 1 meter distances are given between their centers. Right, find the force in Q1 due to the other charges. Now the equation that we have for Coulomb's loss is F is equal to K, Q1, Q2 over R squared. There are only 2 Q's in that equation. So what do you do when you have more than 2 charges? In this case, we have 3. Rid of some extra lines there. Remember back when we solved gravitational force problems and you had maybe 3 or 4 masses and you had to find the force of one mass due to the others? Right, Emily, you remember what you did?
Find the force exerted first charge by the second, by the third charge.
Yeah, you kind of have to do it individually. You say, what's the second charge doing to the first one? What's the third charge doing to the first one? Then we have to do some vector addition. Yeah, so Emily, which one do you want to do first? You want to look at what 2's doing to 1 or what 3's doing to 1?
That was the second one.
Okay, let's look at what force charge 2 exerts in charge 1. And the force that 2 exerts in 1 is going to be K, which is 9 times 10 to the 9th Newton meter squared per Coulomb squared, times the absolute value of Q1. Q1 was 1 microcoulomb, Q2 was 2 microcoulombs, divided by the distance between them squared. And the distance between Q1 and Q2 is 1 meter. And if I do that, I'm going to get the wrong answer. Already made a mistake that's going to make this come out wrong. And you see it, Alex?
The microcoulombs need to be in coulombs.
Yeah, the microcoulombs have to be in coulombs or they're not going to cancel out the coulomb squared and the units for the constant. So you got to be careful with that. That's going to pop up again and again in the homework that you do. So that 1 microcoulomb, we're going to write that as 1 times 10 to the negative 6 coulombs. And the 2 microcoulombs we're writing as 2 times 10 to the negative 6 coulombs. Because if you do that, then the coulomb squared is going to cancel. The meter squared is going to cancel, and you're left with newtons. All right, so what do we get if we do the math there? 9 times 10 to the 9th times 1 times 10 to the negative 6 times 2 times 10 to the negative 6 divided by 1 squared. It should get about 0.018 newtons. Now that's the easy part. The hard part is coming up with the direction. Put it this way, the part that requires thought is coming up with the direction. Anybody can plug numbers in calculators, right? But what's the direction of that force? Right, Sean?
Away.
Okay, away, because like charges, we're talking Q1 and Q2, they're both positive, so they're going to repel each other, they're going to go away. So are we talking about the downward for Q2 or the upward for Q1?
Upward.
Upward for Q1, why upward? We're trying to find the force on which charge? On Q1. We really could care less about Q2. Our interest is what happens to Q1. Answer, the positive charge below it is going to repel it upward. All right, so the direction of that force is upward. Okay, what's next? We've done that. Next step. Lincoln, what would you do next?
Find the first charge. On the first charge.
Yeah, fine. What's the effect of charge 3 on charge 1? And that's going to be K, 9 times 10 to the 9th newton meters squared per Coulomb squared, times Q3. Now Q3 is negative, but remember we take the absolute value of the charge. So we make it positive 3 times 10 to the negative 6 coulombs. That was Q3 times Q1, 1 times 10 to the negative 6 coulombs, divided by, what's the distance between 3 and 1? Do we know that? We can find it, that's right. The distance between 3 and 1 would be that distance. And can we just call it out without doing a whole lot of work? Right, Hillary? Yeah, it's got to be the square root of 2 because this is a 45, 45, 90 triangle. So the hypotenuse is always the square root of 2 times the legs. Right, so the length is the square root of 2, but we got to square that distance. Remember, it's divided by r squared. So we're dividing by the square root of 2 squared, which is just 2. And what's that give us? 9 times 10 to the 9th times 3 times 10 to the negative 6 times 1 times 10 to the negative 6 divided by the square root of 2 squared, which is just 2. And hopefully you can check me on this. I'm getting 0.0135 newtons. Does that check? What's the direction of that force? We're finding the force on Q1 due to Q3. So, Lauren, what would you say? Q3 is going to do what to Q1? It's going to pull it downward because opposites attract. So it's going to get pulled downward along that black line towards Q3. So it's going to get pulled down and to the left. So our direction is down and to the left. Now, can we be more specific than down and to the left? Do we know what angle that's going to be?
45.
It's going to be 45 degrees because we know this is a 45-degree angle right in here. Yeah, so it's going to get pulled down at an angle of 45 degrees to both the vertical and the horizontal. Both of those angles are 45 degrees. So to kind of summarize, Q1 is being repelled upward by Q2, but it's being pulled down and to the left by Q3. Now, how do I figure out what the overall force is? Because the problem doesn't say find the individual forces. It says find the total force on charge 1. So now I have... Yeah, now I have a vector addition problem where what I need to do is to add this vector to this vector. And Sean, you're looking at them as saying that I can't just add the numbers together because they're not in the same direction. And the only way I'm really going to be able to do it is if I take this force right here and split that into components. All right, so that's the next step. Let's go ahead and do that. That 0.0135 Newton force was down and to the left. It has a component that's to the left, and it has a component that's down. And we know that angle is 45 degrees. So we can use trig to get the components. We know the cosine of 45 degrees is equal to the adjacent side, the x component, over the hypotenuse, the 0.0135 newtons. So the x component should just be whatever 0.0135 newtons times the cosine of 45 degrees is, and I'm getting 0.00955 newtons for that. Right, that's the x component. Notice it's to the left. What's the y component going to be? Given the fact that's a 45-degree angle, y component has to be the same thing, doesn't it? It's a 45, 45, 90 triangle, so the y component's also 0.00955 newtons, but that's directed downward. And by the way, does what we're doing now have anything to do with new learning with electricity? It's just a vector addition problem, isn't it? This goes all the way back to October of last year. Well, the beginning of this school year. Yes, this is nothing new. We're just reviewing at this point. All right, so Sean, you said we had to split up into components. We just did that. And what's the next step then?
Add the downward moment to the
Yeah, we got to get the sum of the forces in the x direction, and we got to get the sum of the forces in the y direction. In the x direction, we have this 0.00955 newtons to the left. I'll make that negative since it's to the left. Did the other force have any component in the x direction? No, the other force was 0.018 newtons upward. So that's the only thing horizontally we have. But vertically, we have the negative 0.00955 newtons from the second force. But then we had the positive 0.018 newtons from the first force. Right, this was the F31, this is the F21. So if we add those two together, that should give you about 0.00845 newtons. Positive, which means it's upward. Right, so we added the x's, we added the y's. Once you've done all that, what's the final step? What do I do with the sum of the x's and the sum of the y's? Now I got to draw a triangle, right triangle. And it doesn't matter which one you start with. I'm going to start with the sum of the x's. It's negative. That means I go to the left. So 0.00955 newtons added to positive y direction 0.00845 newtons. So the thing I'm after, the net force, the sum of the different vectors, is going to be whatever that black hypotenuse comes out to be. And Pythagorean theorem says if we add 0.00845 squared to 0.00955 squared and take the square root of all that, that should come out to be about 0.0128 newtons. Am I done? Problem said find the force on Q1. Isn't that it? 0.0128 newtons? What am I missing yet? I need the direction. Yeah, I can see from my diagram it's up and to the left, but I need to know what direction that is. And we can use trig to get that. Because we know the tangent of that angle is the opposite side, 0.00845, over the adjacent, 0.00955 newtons. So whatever the inverse tangent of that is, 0.00845 divided by 0.00955. Looks like theta is about 41.5 degrees. And now I'm done. I know the force is 0.0128 newtons directed up and to the left, 41.5 degrees to the horizontal. So what that means is if I let that charge go, initially it's going to move in that direction. It's going to start moving up and to the left 41.5 degrees to the horizontal under the influence of a force of 0.0128 newtons. question I have for you is, initially, it's going to move in that direction up and to the left. Is it going to keep moving in that direction? In other words, can we predict where it's going to be 5 minutes from now? It keeps moving up and to the left at 41.5 degrees? No. Why would it only move that direction initially? Why would things change, Sam, very quickly?
Because the distances are changing.
Yeah, as soon as this thing starts moving in that direction just a little bit, then it's no longer the distances we calculated, everything changes. So if you want to predict the path of this thing over time, it's a nasty problem that on a spreadsheet, in Excel, here's what you would do. You would calculate the force just like we did. Knowing the force and the mass of this thing, you'd calculate the acceleration. Based upon that, you'd figure out, well, how far does it move maybe in a thousandth of a second? You'd plot the new position. You calculate the new force, calculate the new acceleration, the new angle, right? And figure out how far does it move in the next 1,000th of a second. Plot the new position. See that? On a spreadsheet, it's actually fairly easy to do. And then you wind up with probably some kind of curved path that it would follow as it goes through space. Okay. Any questions about any part of that example that we did? I'm going to change up one little part of it. Let's say that now we momentarily connect Q2 and Q3. Those are the charges at the bottom there. What would happen if we momentarily connected them together with a wire? And then we take the wire away. Right? So we connect them together just for an instant, then we take the wire away. And the problem says find the new force on Q1 due to the other two charges. And we're not going to calculate this one the whole way out, but we are going to talk about how you would approach it. So let's go back to our picture. Bless you. Here's what we're saying. See if I can get this about right. We're connecting this charge to that charge with the wire. Right, this black thing, and here's the wire it's connecting the two. When they're connected together, is the charge going to stay exactly where it was in Q3 and Q2? We're making the assumption that both of these charges have the same physical size. Right? So if these are metal spheres, the size of the Q3 sphere is the same as the size of the Q2 sphere. So why would the charges not stay right where they are? Trip, any reason you could think for or why the charges might flow at all?
They've got something.
Okay, it's true, they have a way to get from the one to the other, but if I'm a negative charge on Q3, why would I not be perfectly content to stay where I am? Because opposites attract. So I see that +2 charge over there, and I'm going to go over towards it, right? Let me ask you guys this. What if this were -2 microcoulombs in Q3 and +2 microcoulombs in Q2? If it were -2 and +2, you connect them together with a wire, what would happen? Huh? They're going to meet, and what's the net charge in each sphere going to be when we're done? It's going to be neutral. Yeah, they would completely cancel themselves out. Now, in this case, are they going to completely cancel? Now, if you add the two together, if we have -3 from the one, and we allow it to mingle with +2 from the other, what's the net remaining charge going to be? You're going to have -1 left over, aren't you? Just a matter of doing the math. Now, think of it this way. -2 of the 3 is going to completely cancel that part out from the +2, but you're still left over with a charge of -1. So the net charge is that. Now, does that net -1 charge remain on that sphere? You're going to wind up with -1 on the left and 0 on the right? Right, Sam?
Would it divide evenly?
It would divide evenly because leg charges repel. It's not going to all stay bunched up. So it would divide evenly, so the new picture would look something like this. Down there at the bottom, here's our Q1 where it was before. But down here at the bottom, these two charges, they're both going to be minus. And Sam, how much in each one?
Half.
Yeah, -0.5 a microcoulomb on each. So when you add them together, you do get the net charge of -1. And then you'd solve the problem all over again, which we're not going to do. Now, it would look a lot like what we just did before. The main difference is Q2 used to be pushing upward on Q1. And you see now that Q2 is going to be pulling downward on it. So the force between 2 and 1 would now be in a downward direction because the opposite charge would attract it. But 3 would still do the same thing to 1 that it used to. It would be pulling it down and to the left. Let me ask you one other thing. What if Q3 physically were a larger sphere than Q2 and we connected them together with the wire like we did before? The net charge when you add them together would still be -1 microcoulomb, but would you have an even split of the charge between the two spheres? Where do you think you'd have more charge? Remember, the charge, like charges repel. They don't like being next to other like charges, so yeah, you get more on the larger one because they can get further apart there than you can in the smaller one. But they'd still have to add together to whatever the total is. And when you connect things together with a conductor, the charge is always going to flow so that positives and negatives are going to cancel each other out. So the next WebAssign, which is the first electricity WebAssign you're going to be doing, these are the kind of problems that you're going to be looking at.